Now that we have a new formula to calculate arc length, let's take it out for a spin and see what it can do. So the formula we just learned was that the arc length of a curve is equal to the integral from one endpoint to the other of the square root of 1 plus the derivative squared with respect to whatever variable we're taking the derivative of and integrating with. So this is the distance between 2 points, which is a line. So we have to figure out what line goes through those 2 points, but then find the derivative of that line. So let's not find the equation of the line. Let's just get f prime of x, which is the slope of the line, which is delta y over delta x, or 4/3. So that means that f prime squared equals 16 over 9. So 1 plus f prime squared is 25 over 9. So we can go ahead and evaluate the integral from 1 to 4, our x values, of the square root of 25 over 9 dx. Well, that's a constant. Not only that, it's a perfect square constant. Square root is 5/3. Integrate that, we get 5/3 x. Evaluate that at 4 and at 1. So 5/3 times 4 minus 1 is equal to 5. All right, well, that's not so bad, but it was a little bit weird. Let's use two methods. The other method would be just the plain old distance formula, right? Well, that's the square root of delta x squared plus delta y squared. And I think we already found delta y to be 4 and delta x to be 3. So we have the square root of 3 squared plus 4 squared. Oh, that's the Pythagorean triple. Okay, cool. So we get the same thing, which is not at all surprising, I hope. Of course, we would prefer the easier method, which is the second method in this case, but that method is only good when we have a linear path. So let's try a nonlinear path. So we'll start with finding the derivative of this function. Well, actually, we'll start by rewriting the function so that it looks a little bit friendlier for derivative purposes. So when we take the derivative, it's just the power rule. So we get 1/8 times 4 is 1/2 x to the third. We've got 1/4 times -2 is -1/2 x to the -3. And we're going to square that, but it might be easier if we factor out the GCF first. That just might make things a little bit easier for our squaring purposes. Get all the messy stuff in one place in one term. So when we square that derivative, we get 1 over 4. We've got x to the -6. And we've got squaring this binomial as x to the 12th minus 2x to the 6th plus 1. All right? Well, we can rewrite this. I guess we can make it a fraction. The numerator is that perfect square trinomial. And in the denominator, we've got 4x to the 6th. All right? Well, if we want to add 1 to this, which we do for our formula, we're going to add 1 to this. Well, that's 4x to the 6th over 4x to the 6th. So that's going to be, 4x to the 6th minus 2x to the 6th is plus 2x to the 6th. We're going to change this minus to a plus. That's a very convenient little switch. Oops. Very convenient little switch from a -2 to a +2. If that's the only change, then we can refactor that perfect square trinomial. It's still a perfect square trinomial. We just changed that minus to a plus. So this is going to be x to the 6th plus 1 squared. And lo and behold, the bottom is also a perfect square. This is 2x cubed squared. So when we integrate to get s, we're going to integrate from 1 to 3. And we're going to take the integral of the square root of 1 plus the derivative squared. When we take the square root of that, we get x to the 6th plus 1 over 2x cubed. Okay, well, we can do that. We'll take the 1/2 out, make sure that 2 stays in the denominator. We'll divide each of the numerator terms by x cubed to get x to the 3 plus x to the -3. And that's ready to integrate using the inverse power rule. X to the 4th divided by 1/4 and x to the -2 divided by -2. And we'll evaluate that at 3 and at 1. Now that's a little bit messy, so maybe there's some nice algebra we can do, like perhaps we'll factor out the GCF here, which would be maybe the nicest thing to factor out would be 1 over 4 times x to the negative 2. Well, I guess I'll leave the x in there. I'll just factor out the 1/4, since I'm going to have to plug these in anyway and subtract and everything. So I'll just leave it like that. Evaluate, well, we'll be left with x to the 4th minus 2x to the negative 2. Evaluate that at 3 and 1. So that's 1/8 times, we've got 3 to the 4th minus 2 over 3 to the 2 minus 1 minus 2. All right. It's a bit of a pain, but we can deal with that, I guess. So one thing we can do is we can find a common denominator here, and that would be 3 squared. So 3 to the 4th times 3 squared is 3 to the 6th minus 2 over 3 squared. Well, that's just 9. Minus negative 1, so plus 1. Almost there. 1/8 times, well, common denominator here would be 9. So 9 plus negative 2 is positive 7. 3 to the 6th plus 7 over 9. Whoops. And you wouldn't believe this, but 3 to the 6th plus 7 is a multiple of 8. It's actually 92 times 8. So the 8 and the 8 cancel out, and we're left with a 92 on the top and a 9 on the bottom. And we can double check that in a calculator. And when we do, hopefully, if we check it in the calculator, we'll find that our answer is one and the same. And I happen to have some worked out calculator work that I'm trying to drag into the screen, and it's not letting me. Here it is. And lo and behold, according to our calculator, it is 92 over 9 for our final answer. That would be the length of that curve. Fantastic. All right, so notice that all you have to really do is type this into the calculator and then refer to this later on. You can play around with your calculator of choice and you can see what it gives you. It might give you a decimal version instead of the fraction, but the decimal should be equivalent to the fraction. Alrighty, so let's try one more example of an arc length problem. This time, our function is 3/2 x to the 2/3, so the derivative is actually pretty nice because the 3/2 and the 2/3 cancel out. We get x raised to the 2/3 minus 1 is negative 1/3. So when we square our derivative, we get x to the negative 2/3. When we add 1 to our derivative squared, we get 1 plus 1 over x to the 2/3, or x to the 2/3 plus 1 over x to the 2/3. So when we integrate to find s, we're going to integrate from 1 to 27 of the square root of x to the 2/3 plus 1 over x to the 2/3 dx. Now in this case, I don't want to actually divide each of these by x to the 2/3. That would actually just take us back to this. I'm going to take advantage of the fact that this denominator is a perfect square. So I'm going to go ahead and factor out that from the denominator. That's x to the 1/3 in the denominator outside of the square root, and that leaves us with no more fraction inside the square root. So that's definitely a little bit simpler. And we're going to use the fact that we know that the derivative of x to the 2/3 is going to put an x to the 1/3 in the denominator and do some clever u substitution. We're going to let u equal x to the 2/3 plus 1. That's a pretty standard thing. Let it equal the argument of a composition of functions. So that means that du dx is equal to 2/3 x to the negative 1/3. So if I solve for dx, I'm going to get 3/2 x to the 1/3 du equals dx. So when we substitute that, let's use a new color now. Integrate from 1 to 27, but that was with x, so 1 to the 2/3 plus 1 is 2, and 27 to the 2/3 plus 1 is 10. And then we have, let's see, we've got 1 over x to the 1/3 times the square root of u times dx, but dx is 3/2 x to the 1/3 dx. And would you believe it? What are the odds? This x to the 1/3 cancels out with this x to the 1/3, and I made a typo here, a righto. There should be a du, right? It's the du right here. I'm replacing dx with all of this. So this 3/2 is a constant that can come out front. We'll integrate from 2 to 10 of u to the 1/2 du, and that's a fairly basic one, right? We'll take 3/2, and then this u to the 1/2 turns into add 1 to the exponent to get 3/2, divide by that exponent. So you get a 2/3, which is kind of fun because the 2/3 and the 3/2 cancel out, just like they did at the beginning, kind of neat. So we get u to the 3/2 evaluated at 10 and at 2. So we can write that as 10 to the 3/2 minus 2 to the 3/2. I might prefer to write it as 10 root 10 minus 2 root 2, but either way is fine. Now, we can also check this in a calculator, and we'll find out that that will also work out. If we see that, let's scroll down so there's not an overlap of stuff so we can read it a little bit better. It gives us the decimal version, but then if we type in our exact answer, we see that it gives us the same decimal answer. So that seems pretty good. A couple things I'd point out about this. The integration is only going to be possible for very particular sorts of functions, right? Like if I changed, for example, this function up here to, I guess maybe we just changed this to a 3 instead of a 4, then this nifty little trick right here wouldn't have worked, and our integration would have been either extremely difficult or perhaps impossible, and we would have had to resort to a calculator. So don't be afraid to pull out your calculator to evaluate these integrals if you get stuck with the analytic side of things. Okay, these are pretty commonly these will pretty commonly show up on the either setup but do not evaluate section of a test, or perhaps on the calculator portion where you just type it into the calculator and get a decimal answer. So give it your best shot to try to integrate these integrals, but if you get stuck on them, then there's no shame in pulling out your calculator.